Hello there. So the first quarter of your physics sequence, which was mechanics, focused on forces between objects. Remember the Newton's three laws. Newton's first law, if you don't apply a force on an object, it won't accelerate. Newton's second law, if you do apply a force on an object, it will accelerate. And here's how you calculate it. A equals F over m. And Newton's third law, that anytime a force acts on an object, then in return, that object exerts an equal and opposite force on the other object that created the force in the first place. An issue, though, that we avoided was, what do we mean by an object? We didn't really define any such thing. We just took objects, everyday items that you're familiar with, blocks and cars and trains and balls and similar such things, and then just assumed that you understood what we meant by those things, and then we talked about what happens to them when you apply forces on them. They accelerate and so on. But the question of what exactly an object is was, as I say, left undiscussed. And reasonably enough, because as it turns out, the question of what an object is, and for that matter, once we've defined an object, what can we say about the forces on this thing that we call an object that is more complicated than we realized? What can we say about the forces involved? And the answer to all those questions turns out to be complicated, sufficiently complicated that in fact we have an entire course devoted to pretty much answering just those two questions. So we're going to start in on dealing with those questions and with the beginnings of the answers to those questions. And I don't think I'm going to be surprising you terribly by telling you, first off, that the answer to the first part of the first answer of the first question, what is an object, is that an object is a construct, a collection of molecules, usually, or sometimes just atoms. But of course, molecules are in turn constructed from atoms. I'm going to more or less assume that you more or less understand those ideas more or less. However, there are a few issues involved with atoms that are going to be crucially important for understanding everything that we do for the next little while. So just to make sure we're all on the same page, I'm going to start off by simply discussing the basic properties of atoms, and somewhere along the way I will sneak in a new idea, and that new idea will be the central idea that will occupy our time and attention for the next several lectures. Okay, so the idea is I'm going to define an atom. I'm going to describe for you the structure of an atom, and then I'll say, okay, as I just did, then we can take a collection of these atoms, construct more complicated collections of them, and those more complicated collections of atoms, we'll call those molecules. I'll give you a little more detail on that. And then if we have a big enough collection of molecules, then we call that big collection of molecules an object. So that's kind of the hierarchy there. So atoms to usually molecules to objects, and then once we have an object, then we can talk about the forces that we talked about in the first quarter of your physics course. All right, so an atom, now it turns out that an atom is an extraordinarily complex construct. I was going to say object, but maybe I better stick with the other meaning of object here. An atom is extraordinarily complex, so there's a lot of bits and pieces to it, far more than we're going to discuss in this course. We'll start, however, with the simplest model of an atom, which is still extraordinarily useful, and that is that our atom is constructed from three primary particles. And again, probably you know an awful lot of this. You may know all of this, but this way, at least for our, I'm certain that you've heard all of this. So constructed from 3 particles. And I'm putting a note here just because I'm intellectually honest with you. There's actually lots and lots of particles that go into making up an atom. But the 3 that I'm going to talk about are the most important ones, at least for our purposes. Those 3 are the proton, the neutron, and the electron. Most of the properties that we are going to discuss in this course can be understood from considering just these 3, and indeed, for the most part, pretty much every question that we're going to ask in this course can be answered by only considering the proton and the neutron. The proton and the neutron together bind together, meaning that they they stay close to each other by some sort of a force. And they form the center, the nucleus of the atom. The electron, on the other hand, does not exist in the nucleus, and it orbits the nucleus. Now, exactly how it orbits it and why and what the forces are involved and so on, we'll discuss to a certain extent. We'll discuss an awful lot about the force that causes the electron to orbit the nucleus. Yeah, I don't think I'll just leave it at that. All right, so that's that. And so the general structure for the atom is in the, again, simple model. The typical atom is generally drawn like this. So we have a bunch of protons all close to each other, and mixed in among them are well, I shouldn't say that. Mixed in among them is some number of neutrons. In what I was going to say is in small atoms, by small I mean low mass atoms, typically the number of neutrons is essentially equal to the number of protons in the nucleus. As the atom gets larger and larger in mass and in physical size, that stops being true, and it ends up being that we get a lot more neutrons in an atomic nucleus than there are protons. But again, the neutron is, for the most part, not going to concern us in this course. I'm mentioning it now for completeness, but pretty much after this lecture, we will very rarely care about the nucleus. You will care very much about the nucleus in your 3rd quarter physics, or anyway, when you study nuclear physics, atomic and nuclear physics, the neutron will become crucially important. But for us, in this course, not so much. And then the rest of our model is that there are distributed at various distances around the 2, 3, 4, 5, 6, 7, 8. That's actually too many. 1, 2, 3, 4, 5, 6, 7, 8. That's right. And then 1, 2 there. Okay, good. Yeah, so distributed in space at various distances around the nucleus are the electrons. Okay, and so this is the way the atom is typically pictured in sort of the basic model. Now, there's a number of things that have already crept in here that I haven't bothered to even mention, let alone explain, but I will do that. And the thing that I'm looking at now, there's a lot of things, but the ones that I put in here that I haven't explained why I did them, but the ones that I want to mention right now for you to start thinking in the back of your minds is that the electrons here, I drew them with little negative signs, the protons with little positive signs, and the neutrons with no sign at all. Is there any significance to that, other than making sure that you can tell the various particles apart from each other? And the answer is yeah, there's a lot of significance to that. And I'll mention that in just a moment. Okay, so that's usually the way you see an atom drawn, although another thing that often gets thrown in is in the usual diagrams of atoms that you see, people will end up drawing imaginary circles in the places where the electrons can be. And in the drawings, they are usually careful to, and I will be too, careful to show that the electrons are at specific distances away from the nucleus. And it turns out to be the case. It's not going to matter to us in this course, but again, it will matter to you a great deal later. But it turns out that the electrons in the atom, they can be at certain distances from the nucleus, and they cannot be at any other distance. And so, for example, I can have these two electrons can be this close to the nucleus. These 8 electrons, in turn, can be this close to the nucleus, but it turns out that it never happens that any electron is ever, let's say, halfway between these two distances. And why that's the case is a question for quantum mechanics. Again, a different course. We're not going to worry about that in this course. But since it turns out that electrons can never exist, will never be found in this region here, that's the reason for these dashed lines. They're just imaginary lines letting you see where the electrons can be versus where they cannot be. Yeah, so this dashed black line here is purely imaginary. Okay, so that's what the atom looks like, at least in simple diagrams. The next thing I want to mention is some important physical properties of these 3 particles. And I chose the word properties there. Let's talk about the properties of these particles. And I want to remind you that a property of an object, or more correctly, the collection of properties that an object has, that a particle has, is what defines the particle. And it is simply part of the definition, part of the meaning of certain object. And so if I talk about the volume of an object, or the temperature of an object, or the color of an object, or the mass of an object, these things are all inherent properties of a particular object. And by the way, I'm no longer using the word object the way I did at the beginning of this lecture. Now I just mean, when I say object, I mean anything. And so it could be protons or neutrons, it could be atoms, it could be buses, whatever I happen to be talking about. So the concept of a property of an object is what helps define what that object is. And in the case of our proton, neutrons, and electrons, the properties that I'm going to care about at the moment I'm going to list them here. First of all, let's start with the proton. Its mass. Protons are what we physicists call very, very small. That was a joke. The mass of the proton is 1.6725 times 10 to the minus 27 kilograms. Okay, and I just realized that I better check that number. So I'm going to pause the recording and check to make sure I got that number right. I just pulled it out of my memory, and since I'm recording this, I better get this right. So I'm going to pause the recording. It turned out it was a good thing I checked. I was off just by 1 digit, but I was off slightly. 1.67265. Okay, 1.67265 times 10 to the negative 27 kilograms. A couple of things to notice about this. 10 to the minus 27 kilograms. Really, 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 with lots more reallys, small mass. Also, please notice 1, 2, 3, 4, 5 decimal places of accuracy, or precision, I should say. We know the mass of the proton pretty accurately. Okay. There's another property of the proton that I'm going to mention, but I'm going to skip onto the neutron here. Its mass, which I will label n sub n, is 1.67500 times 10 to the minus 27 kilograms. And take a quick look at those numbers, and you'll see that the neutron has very slightly more mass than the proton. Once again, the neutron is going to be of very little concern to us in this course. It is interesting to note that the neutron and the proton have masses that are so very, very close to each other. Won't matter to us in this class, but it's that tiny, tiny difference in mass is going to be hugely important when you study nuclear physics. Okay, and then the electron, by contrast, its mass, m sub e, is 9.11 times 10 to the minus 31 kilograms. Okay, and so you see that the proton and neutron have masses that are over 1,800 times larger than the mass of the electron. At the risk of getting ahead of myself, the practical consequence of this fact is that when we start talking about moving these objects around, exerting forces on them, causing them to accelerate, causing them to move around, doing work on them, and so on, what we will find is that for a given force, the electron's acceleration will be more than 1,800 times as large as the acceleration that the proton would have subjected to that same force, and that's going to have very big practical consequences for us as well. So anyway, so the masses for the proton and for the electron are very, very different from each other. Okay. I mentioned that well, I just mentioned about exerting forces on these things. Now, the masses of these things are so tiny, and so you might guess, and again, I'm sure you know this, but anyway, you might guess from how small these masses are that the objects themselves, their physical size, their diameter, or anyway their dimensions, are correspondingly also very small. And if you think so, then your instincts are exactly correct. These things are absolutely, excessively tiny. They're among the smallest things in the universe, and quite invisible to human eyes. We have to investigate them, measure them, determine determine their properties, work with them through very indirect means. And the primary means by which we interact with them is by applying forces on them and seeing what happens when we exert forces on them. Okay? But then that leads to the next question: is what kind of forces do we apply? Do we put gravity on them? Do we do friction? Do we do tension forces, spring force? What do we do? Right? Think about all those forces that you studied back in your first quarter of physics. And so if we want to apply force on something this tiny, how do we do that? And in fact, the answer to that question is fundamental to everything that we're going to do. And the force that we apply is going to be a consequence of another property that protons and electrons have, but the neutron does not. And what that property is, how it acts, how it works, how we measure it, and how we talk about it will be the subject of the next lecture.